So this is the Waves Homework Booklet question 26, and we've got a plane transmission diffraction grating. The diffraction grating for the first order beam is lambda is d sine theta. We're also used to using n lambda equals d sine theta, but in this case we've got n equals 1. The figure below shows two slits in the grating. Label the figure below with the distances d and lambda. Really important that you read everything, because otherwise people will end up not actually doing this, and I also had a number of people that labelled d but not lambda. So d is defined as the distance between the centres of two adjacent slits, so it can be marked on very straightforwardly there. And then really remembering from the derivation that lambda is the distance, the extra distance that one path coming from the grating has travelled compared to the other. So that's giving me a path difference of lambda. That's meaning the two waves will be in phase, and therefore we will get a first order maximum in that direction. So that distance there is lambda. State and explain what happens to the value of theta for the first order beam if the wavelength of the monochromatic light decreases. State and explain. It is important that I do both of those to get the marks, therefore. Go back to the equation. Lambda is d sine theta. So if lambda decreases, d stays the same, sine theta will decrease, therefore theta decreases. That's what I've got here. So lambda's getting smaller, and d is constant, lambda's smaller, sine theta must get smaller, so theta gets smaller. Generally, it's not a great idea just to be answering in terms of smaller and larger, but we haven't got any option here because we're not told by how much the wavelength has changed. The other way of viewing it would be to get the first order beam now. I need that distance, which is marked on the diagram as lambda. That's obviously a shorter distance, and the way that I get that shorter distance would be to rotate these two beams round to a smaller angle, in other words to make theta smaller. So that's another way I could give the explanation there. I need a smaller path difference showing on the diagram, which I'd achieve with a smaller angle, because the path length to get the first order maximum needs to be one wavelength. Diffraction grating was used with a spectrometer to obtain the line spectrum of star X shown in the figure. Shown are some line spectra for 6 elements that have been obtained in the laboratory, and put ticks in the boxes next to 3 elements that are present in the atmosphere of star X. So if we have a look at this diagram, here's the spectrum for X, and then we've got various other ones, and all you need to do, maybe using a ruler running in that direction, is to look at each of the lines that are showing in star X and work out which ones they line up with. And so I've done that with colour. Lines for helium I've marked on there, so I've given helium a tick. Lines for hydrogen I've found, given them a tick, and I've got lines for mercury there, given that a tick. Strontium, calcium, sodium, can't see those lines, can't match them up, not ticked. Diffraction grating used to obtain the spectrum has got 300 slits per millimetre. Calculate the distance between the centres of two adjacent slits, so that's d, and again it's my 1 millimetre, 1 times 10 to the minus 3 metres, divided by 300, 3.33 times 10 to the minus 6. And then finally it's asking us to calculate the first order angle of diffraction of line P on the figure above. Again, we'll use n lambda as d sine theta. We know n is 1. We're trying to find theta. We know d, we've just calculated it. I need to know the wavelength. So if I go back to the diagram, zoom in onto where P is marked, really zoom in here, and if I now try, see if I can draw up a nice vertical line, bring that in, and we can see that we've got 500, 510, 20, 30, 40. It's about it's over 545. It's under 550. We can see there. There we go. That line's gone away. And if we then come back down, so we've got a value there. I'll put 547 into the equation. So sine theta n1 lambda 547 times 10 to the minus 9 divided by d 3.33 times 10 to the minus 6. That gives me again sine theta is 0.1641. Put that through the calculator. I've got an angle of 9.4 degrees. The way the mark scheme worked on this was interesting. It was the first mark was for some kind of substitution with a wavelength that was somewhere between, I think it might have been even 540 and 560. The second mark was for the correct answer, but showing a very accurately read off value of the wavelength. It needed that wavelength to be somewhere between 545 and 548 times 10 to the minus 9 meters. So that is the Waves Homework booklet question 26.